All right, so I'm now going to try to explain to you, this is for physics, CP, and today happens to be February 22nd, 2021. And what I'd like to explain to you in this little lecture section is called Newton's version of Kepler's third law. Okay, so here we go. Uh, Historically, once upon a time, we thought the Earth was the center of the universe. Eventually, Copernicus in the 1500s uh, carried out measurements based on the assumption that the sun was the center of the universe. And from that, he worked out precisely for his day and age the scale of our solar system. So he was able to say, here's the sun in the center of the universe, and going around the sun is Mercury and Venus and Earth and Mars and Jupiter and Saturn, the entire solar system as we knew it back then. Then along came a guy named Tycho Brahe, who built an observatory in Northern Europe, and for over 20 years carried out precise measurements of the positions of stars and planets that he could see in the sky, night after night. He had a laboratory staff, and he would supervise it night after night, year after year. He wanted to analyze it, so uh, uh, thousands of years ago, a Greek philosopher, mathematician, worked out a model for predicting when certain events would take place in the sky. When would you see a solar eclipse? When would you see a lunar eclipse? When would you see a conjunction where two planets seem to be next to each other in the sky? And for thousands of years, his model worked pretty well. But by the 1500s, 1600s, the model was off by about a day and a half. And the rising mathematicians and astronomers of the day wanted to tweak up the model and make it more correct again, the way it used to be 2,000 years earlier. So Tycho Brahe was one guy who wanted to do it, but he wasn't really that great of a mathematician, perhaps. And he had his own idea that said, no, the Earth is the center of the universe. The sun goes around the Earth, but the planets, other planets go around the sun. So it's a little crazy idea compared to what you guys are taught. Along came Johannes Kepler, who was hired as the assistant to Tycho Brahe. And so in the early 1600s, Kepler said, oh, I'm going to solve this problem. And sure enough, in less than 2 weeks, he worked out an upgrade to the ancients model that was accurate to within half the width of the full moon as you look up in the sky. So it was off by a quarter of a degree. And Kepler said to himself, you know what? I know Tycho Brahe collected data that was of such high quality that I'm going to reject my solution as being not the best it can be, not the correct solution. So then he dedicated himself to figuring out what really happened. It took him 10 years and something like 500 sheets of papers of calculations. But eventually, he realized that with the sun in the middle of the universe and the Earth going around the sun, which he assumed was a perfect circle, he was able to look at data that Tycho Brahe had collected for the planet Mars. And he said, okay, I know where Mars is. I know where the Earth is each day of the year. I know how long it takes Mars to go around the sun once. So he observed Mars according to the notebooks when it was at the same point in space on different dates as viewed from Earth. And so with that information, he was able to triangulate and calculate where is Mars relative to the sun. So he did that for about 9 different points around the sun. and then did a best fit curve and established, hey, Mars isn't on a circular orbit at all. It's on an ellipse. And so Kepler developed three laws of motion. And the first one says something like the planets travel in elliptical orbits around the sun, and the sun is at one of the two focal points of the ellipse. So that's his first law. And you don't care today. His second law said a planet sweeps out equal areas in equal amounts of time. And that just means when a planet is close to the sun, it's going faster. When it's far away from the sun, it's going slower. And when you calculate how much area is swept out by its orbital radius, it's the same value for equal amounts of time. So we don't really care about his second law either. But his third law found a mass relationship between the distance of the planet from the sun and the time that it takes for it to go around the sun once. And that's called his third law. And he said the period squared is proportional to the semi-major axis cubed. So there's Kepler's third law. And that's my crude way of writing the proportionality symbol from math class. The orbital period squared is proportional to the average distance from the sun cubed. He calls it the semi-major axis of the ellipse. Kepler figured this out in the early 1600s. Just after that, and kind of overlapping in time, is when Galileo invented, well, he didn't invent, but built a telescope and used it for looking up into the sky and reporting what he observed. So Galileo discovered that there is the planet Jupiter that actually has four little moons going around it that he could see in his telescope. And if you measure the distance that the orbit is and time how long it takes to go around, it follows the same law. Kepler was so excited. He said, Galileo, please respond to my letters confirming that my equation here is correct. Galileo never did because he was terrified of being burned at the stake as a heretic for saying that the sun was the center of the universe instead of saying that the earth was the center of the universe. So religion and science had kind of a clash going on at that time. Galileo grew old, died. I'll tell you some more stories about him some other time. After he died, then Isaac Newton was born. And Isaac Newton developed his universal law of gravitation. The force of gravity is equal to G times M1 times M2 divided by the distance from the center of one object to the center of the second object squared. He also developed a formula for the centripetal acceleration, m times v squared divided by r, which we can also write as m times 4 pi squared times r divided by the period squared. So what I'm going to do in this little lecture is make the connection between these two guys. And it goes like this. The Earth goes around the sun. The sun and the Earth attract each other because of Newton's law of motion, or Newton's law of universal gravitation. The Earth wants to just go off at a tangent, but doesn't because there is a centripetal force pulling the Earth into a circle. If the force of gravity were greater than the centripetal force, then the Earth would spiral into the sun, we would all burn up and die. If the force of gravity were less than the centripetal force, then the Earth would fly off and spiral away from the sun. We would all freeze to death, like people in Texas, and die. Well, So 5 billion years later, we haven't burned up, we haven't frozen, we're still orbiting the sun. So you can conclude that the force of gravity between the Earth and Sun is equal to the centripetal force acting on the Earth. So mathematically, I can write G times M1 times M2 divided by R squared can be set equal to M times V squared divided by R. Okay, I'll do this one next, but for now, let's just see what this says. This says the mass of the Earth cancels out, and what matters is the mass of the Sun, or the central body, as I'm going to call it. And one of these two radii cancel out. So here is the equation for the speed of an object in uniform circular motion in orbit around some central body. It is the product of the universal gravitational constant, capital G, times the mass of that central body divided by the orbit radius. So for example, if I had a mass of 3.10 times 10 to the 18th power kilograms, so an asteroid, and I were a distance from this asteroid, from the center of this asteroid, of about 575 meters, and I don't even know if I can get that close to this asteroid without bumping into it. But according to the formula, if I could get that close and orbit it, that would be the square root of G, which is 6.672 times 10 to the negative 11th power newtons meter squared per kilogram squared, times 3.10 times 10 to the 18th power, divided by 575, and it says the orbital speed would be 600 meters per second. So 3 sig figs. So great. This is a formula that relates orbit radius r orbit speed v and central body mass m to each other. So as with any physics problem, if I have an equation that's got three variables in it, I give you any two of them, you solve for the third. I give you r and v, you solve for m. I give you v and m, you solve for r. I give you r and m, you solve for v, and that's how you get better than a b. But wait, there's a second way of expressing centripetal force, and that came about because when you have a circle of radius r and you're going at speed v, the distance that you travel when you go around the circle once, the distance is 2 pi r, the circumference of a circle. And the amount of time it takes you to go around the circle once is called the period. That's capital T. You might remember from one-dimensional motion that distance equals speed times time. Well, this relationship applies in a circle as well. The distance is the circumference. The time is the period. And the speed is the speed that you're moving along in this circle. That's where this second equation comes from for centripetal acceleration. Centripetal acceleration said v squared divided by r. If I substitute 2 pi r divided by the period for v, now it's 4 pi squared r divided by t squared, because one of the r's will cancel. Multiply that by the mass, and you have centripetal force is equal to m times 4 pi squared times r divided by t squared. Here is where this becomes the second equation. So Newton's version of Kepler's third law says, I'm going to take this equation for centripetal acceleration and set it equal to the force of gravity between the two of them. So G m over r squared is equal to, now this mass is the mass of what is orbiting the central body again. So I'll write that as lowercase m, and I'll use capital M for the mass of the central body. So m times 4 pi squared times r divided by t squared. I'm setting the force of gravitational attraction between two objects equal to the centripetal force needed to keep one of those objects in orbit around the other object. You should notice that the mass cancels for the object that is in orbit. So if we're talking about the Earth and the Sun, it's the mass of the Earth that cancels. If we're talking about the moon going around the Earth, then it's the mass of the moon that cancels. And what do I have left? I have an r squared on the bottom on the left. I have an r on the top on the right. And if you were to cancel one of them, that would be a mistake. Instead, I'm going to multiply both sides by r squared, and that makes it r cubed on the right. I'm going to multiply both sides by t squared. So right now, if I were to write it the way I have it, it's t squared times capital G times capital M is equal to 4 pi squared r cubed. Okay, I'm not done. I'm going to divide both sides by G. I'm going to divide both sides by M. Here is what I have left. The orbital period squared is equal to the product of 4 times pi squared times the orbit radius cubed divided by the universal gravitational constant divided by the mass of the central body. If you think back one page to Kepler's third law, he said the period of a planet going around the sun squared is directly proportional to that orbit radius cubed. Kepler worked in units called astronomical units. So the distance from the Earth to the sun is 1 astronomical unit. And he used years for his period. So for the Earth, 1 squared is equal to 1 cubed. For Mars, the period is a little over 2 Earth years. The radius was worked out by Copernicus, and so was the period. And there's a relationship. Okay, you take the distance from the sun to Mars cubed, and that is equal to the time it takes Mars to go around the sun squared in the units of years and astronomical units. This is from the early 1600s. This is from the early 1700s. So by now, the meter stick was invented. The kilogram was established for the mass. Time was divided up into seconds, not just minutes and hours. So this is called Newton's version of Kepler's third law. But notice it's still t squared is proportional to the orbit radius cubed. So it's still Kepler's third law. It's just now the proportionality constant is replaced with actual values, which means whenever you use Newton's version of Kepler's third law, the radius has to be expressed in units of meters. And the period has to be expressed in units of seconds. And the mass has to be expressed in units of kilograms. Great. But it's still a physics equation. And there's three variables: the period, the radius, and the mass. So just like any physics problem presented to this class, I'll give you two of these values, and you have to go solve for the third one. So I can give you R and T, you solve for the mass. I give you R and M, you solve for T. I give you T and M, you solve for R. Let's practice this equation now. Suppose I have an orbit radius of 10,000 kilometers. Oh man, of course you know that 1 kilometer is 1,000 meters. Suppose I have a mass that I'm orbiting, some central body, and it's like an asteroid. 6.54 times 10 to the, let's make it like 18th power kilograms. And so I could challenge you. Great. What is the period of time it takes to go around this mass when you're in that orbit? Solve for the orbital period. Truthfully, there's two ways you can get to this answer. How so, you ask? We could actually go solve for the orbital speed because we know the mass and we know the radius. We could solve for the speed and then say, oh, I can calculate the circumference, divide that by the speed, and that will give me the period. So you could solve the problem that way. It's legit. I, of course, am going to solve it using Newton's version of Kepler's third law. So the period is equal to the square root of 4, which is 2, the square root of pi squared, which is pi, the square root of the radius, which is 10,000 kilometers, which I have to write as 10 million meters. And I'm going to cube that. So that's 10 million cubed, divided by the universal gravitational constant G, 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared, divided by the mass of 6.54 times 10 to the 18th power kilograms. So 2 pi square root 10, 1, 2, 3, 4, 5, 6 raised to the power of 3 divided by G divided by 6.54 times 10 to the 18th power, enter. There's the orbital period. It says 9,510,000 seconds. to 3 sig figs. Of course, if you divide that by 60, that'll tell you how many minutes it is. 159,000 minutes. If you divide that by 60, that'll tell you how many hours it is. Okay, so this is 2,640 hours. If I divide that by 24, that tells me, okay, here's something I can understand. That's 110 days. Ta-da! Let's do another example. Oh, and by the way, I can also ask you, so what is my orbital speed? And you say, oh, that's simple. That's just gm over r. So the orbital speed is the square root of g times 6.54 times 10 to the 18th power divided by 10. 1, 2, 3, 4, 5, 6 zeros. Enter. And it says your speed is 6.61 meters per second. At that speed, it's going to take you 110 days to travel a circle whose radius is 10,000 kilometers. I mean, you can check. 2 pi r divided by speed will give you this period of time. Let's do another example. Maybe not, since the period is so close to the end. I'm going to close by saying I put up a little YouTube video, and I'm going to explain it here in 1 minute. If I have a circle or a planet, its radius is capital R. I could be some height, h, above this planet. We call that its altitude. And at this altitude, I'm on an orbit. It should be a circular orbit for you guys, not elliptical. The orbit radius, lowercase r, orbit radius, lowercase r, is the radius of the planet, capital R, plus the altitude above the planet. Okay, so I have a short YouTube video that does this drawing with an example or two. I'm hoping that you'll be able to apply this as we go forward in the course.